So far, when you're given the instruction to factor something, your skill that you would turn to first is looking for a GCF. So I want to introduce you to a scenario where that isn't going to work and yet something is still factorable. Let me show you what I mean. You'll see in this string of terms that there are 4 of them, and that if you try to look numerically at something that can be taken out of all 4 of them, it's not possible. This has a 1 in front, a 1 in front, and a 2 and a 2. 1, 1, 2, and 2 are not identical, and they're both prime factors. Similarly, a couple of these have x's and a couple of these have y's, but none of them have any of the literal coefficient being identical. So those are some key things that you're looking for when you need to factor by grouping. You notice that there is no GCF. You also notice that there are 4 terms present, and there's sort of a pairing of commonalities going on. And what I mean by that is, again, 2 of these have 2's, 2 of these have 1's, 2 of these have a's, 2 of these have x's, 2 of these have y's. You start to see some pairings that might be present, okay? So when we factor by grouping, we're going to do exactly as it suggests, and we're going to subdivide the string of 4 things into 2 pairs. And we're going to look for a GCF within each pair. So in this pair, I notice that they both have a GCF of A. And if I multiply A times X, I'll get AX back. If I multiply A times positive Y, I'll get AY back. Okay, and so I have successfully factored the first 2 terms in this string. Let's see if we can do the same thing here. I notice that numerically they have a common factor of +2, or a GCF. So I'm going to take it out. Notice that 2 times x would give me 2x, and 2 times positive y would give me 2y. Now what's really neat in this line is this looks like our previous video, where we now have a binomial as a common factor. So let's take that binomial out as a common factor for each of these. So I'm going to have x plus y, and what does it have to get multiplied by to get this first string of terms back? It needs to be multiplied by a. In similar fashion, what does x plus y have to be multiplied by in order to get this string back? It has to be multiplied by +2. So factoring by grouping takes into account a new step here, and it utilizes our binomial as a common factor step as well in being able to factor to get an answer. Let's look at this example. So again, when we say factor this, our first thing is there a GCF for all 4 terms? And the answer is no. These have some x's in them, that one doesn't. This has a prime factor of 5. This one is a prime factor of 5 embedded in it. But 3 and 9 don't, but they in turn have a prime factor of 3. So there's no GCF. There are 4 terms present, and we see some pairing of commonalities. We see both of these have an x. We see that both of these have a multiple of 5 incorporated in them. These have a multiple of 3 incorporated in them. Okay? So what we want to do then is try factoring by grouping. And so I'm a big fan of putting these brackets underneath just to narrow your sight lines and help you focus. So when I look in this first bracket, what is the GCF, both from a numerical and a literal standpoint? Well, the biggest thing that can go into 9, other than 1 and 9, is 3, and it's also a factor of 15 as well. And then this is an x and this is an x squared, so the most number of x's I can take out is 1 because then this one's depleted. So 3x is the GCF for the first set of terms. What can I multiply 3x by in order to get 9x squared? I can multiply it by 3x. In similar fashion, what can I multiply 3x by in order to get 15x? I can multiply it by 5. Okay? Now, looking at this second string, is there a GCF? And the answer is no. There's not, nothing numerically, nothing literally. So I'm going to take out a GCF of 1. and I'm going to show you why in just a moment. What do I have to multiply 1 by in order to get 3x plus 5? Well, I have to multiply it by 3x plus 5. And you get this really cool scenario again where you end up with a binomial as the common factor. Okay? So we can factor this now, pulling the binomial out. So this is equal to 3x plus 5, and what do I have to multiply it by in order to get this first string of multiples? I have to multiply it by 3x. What do I have to multiply it by in order to get these string of multiples? I have to multiply it by 1. And there you have it. Now it would be interesting to do a little experiment to see if it matters what order the terms are in when you factor by grouping. So I want to show you that the switching of the order won't affect the outcome of your final answer. So let's review one more time. Pair it up, pair it up. The GCF of the first two is 3x, which I would have to multiply by 3x plus 1 in order to get what is up here through the distributive property. Similarly, in these two, I have a GCF of positive 5. And what would I have to multiply 5 by in order to get 15x plus 5? I would have to multiply it by 3x plus 1. Well, hey, here's a GCF. Okay, right here and here. It's a binomial GCF. Let's take it out. And we are left with it having to be multiplied by 3x plus 5 in order to get what we have up here. Now, these are actually identical. This 3x plus 1 is the same as this, and this 3x plus 5 is the same as this. So I got the same answer, I just got a reversal of the multiples, but it doesn't matter what order they get multiplied in, I would still get the same answer. All right, this final example that's in your notes has a couple of asterisks beside it, and I'll tell you why. When we look at it first to see if it's factorable, we look for a GCF, and of course we can see they don't have any numerical or literal pieces all in common, so there is no GCF. There are 4 terms present, and we do see a little bit of pairing going on. In fact, the only pairing really I see is the fact that there is a y here and a y here. Remember in the other examples we saw more pairing of commonalities other than just one. We saw like 2 2's, 2 a's, 2 x's, 2 y's. In here we saw 2x terms. We saw 9 and 3, being multiples of each other, okay? But here there's only one pairing, if you will. So can it be factored by grouping? Well, let's try the same steps that we have been doing so far to see what happens. Is there anything in here that these two have in common? Absolutely not. Okay, so I could do a 1 times ax plus by. Okay, and over here, is there anything that these have in common? No. So I could even do plus 1 and have negative xy plus 10. Now the problem I run into is that this term and this term are not identical binomials. So I cannot factor them out. So what if we tried the same trick that we did above? What if we rearranged the order of a couple of things? What if we put, say, these two x's together? Oh, by the way, we do have a pair of x's here too, so there is another pairing. Let's try putting those together and see if rearranging the order of these terms makes a difference. Well, again, let's do our little trick here. No GCF, 4 terms present, we've got some pairings going on, and let's see. Well, this time they both have an x in common, so we can take it out as a GCF. X would have to be multiplied by a and negative y in order to end up with these two terms above. And then I get over here and I go, again, no GCF, so I'm going to pull out plus 1. This becomes by plus 10. So even with rearranging, I wasn't able to achieve identical binomials in this step. So in this scenario, even though a lot of these criteria were met, I would say as a final answer to a question like this that these are not factorable for reasons that we've just talked about. Okay, they don't meet the criteria of a GCF and they can't have no binomial as a common factor. Okay, and it's possible a lot of things are not factorable. So just be mindful of that in your practice. All right, this concludes lesson 5.3. If you have any questions with the practice, as always, be sure to touch base with me and I'm happy to help.